In today's math lesson, we're going to factor quadratics that happen to be special cases. The first one is to look at perfect squares. So perfect squares come from a trinomial where we realize that the first term and the last term are both perfect squares. To process through this, you're going to take the square root of our first term and you'll get x times the square root of a, which we're going to write a little differently. And you take the square root of your last term, c, and we're going to write this a little bit differently too. But this shows the process of what it is that's actually happening. The result of taking these two square roots is going to give us two binomials where we have our first term that has been square rooted plus the third term that's been square rooted times itself. And you know in mathematics, if you have something that is multiplied to itself, we have a shorthand way to write that, and that is just to write that it is squared at the end of its quantity. So while these two binomials multiplied together really are exactly the same as this one binomial with a squared outside of it, it is important to realize this is just how we show things multiplied to themselves, just squared. So it's the most condensed, most simplified version. Our second special case is the difference of squares, and this looks very different. So let's look at this and find out just how easy it is to work with. This quadratic is actually missing its b term. So it only shows two terms, and what's special about them is that you always have a minus in between them. And you know this is a difference of two squares when you realize that you can take the square root of ax squared and get something very nice and clean. And you can take the square root of c and also get something very nice and clean. And again, that minus does have to be in between the original two terms. So to write our binomials for this set of squares, we're going to have our two sets of parentheses and our x with the square root of a in both of them, and our square root of c in both of them. But in the first set or one set of parentheses, you will have a plus sign, while in the second set, you're going to have a minus sign. So while this might look a little peculiar and confusing at the moment, it's actually going to be really simple, really fast, really friendly. And just for clarification, the difference of squares is only for a polynomial that has two terms. Truthfully, where the b term is missing. It's just the first term and the last term that would be in a normal quadratic, where both of these terms are perfect squares and there happens to be a minus between those two terms. Disclaimer. At the end of this lesson, if you find that either of these methods for these special cases is just way too overwhelming and your head is full and swimming from having other ways to factor out quadratics, then hey, don't sweat it. You can go back to doing the box method that we did in the previous lessons, and you don't have to worry about these special cases. These are just shortcuts that have worked again and again, and they're a nice, faster way to make things happen. In example 1, we see that there are three terms, and as the case would be, 9u squared and 1 are both perfect squares. Let's go find out what happens. So the square root of 9u squared, the square root of 9 is 3. The square root of u squared is u. And the square root of 1 is just 1. So now we can go ahead and very quickly write our final answer. Believe it or not, it happens just that fast. So we know that because there were three terms in the original problem, I'm going to end up with one set of parentheses where the quantity is squared. My first term in the parentheses comes from the square root of my first term in the trinomial so 3u. The second term in my parentheses comes from the square root of my third term in the trinomial. And then something that we didn't mention previously was that whatever the sign is on the second term, that is what you're going to use as your sign here in the middle of your binomial. And there you go. Here in example 2, we only have 2 terms that are visibly showing to us. So we know that this is going to be a difference of squares. So let's look at what our 2 terms give to us to get this problem started. The square root of my first term, k squared, is just k. And the square root of my second term, 4, is just 2. So now we can go ahead and set up our 2 binomials. So remembering, since I only had 2 terms to begin with, that means I'm going to have 2 sets of binomials. The first term in both binomials will be my k, which came from the square root of the first term in our original problem. The second term in both of my binomials is this 2, and it came from the square root of 4. So the big difference with the difference of squares is that one of your sets of parentheses will have a plus in the middle of it, while the other one has a minus in the middle of it. And it's just that simple, just that fast, and there you go. In example 3, we again have only 2 terms, and they happen to both be perfect squares. So let's tear them apart and see what happens. So the square root of 16c squared. The square root of 16 is 4. The square root of c squared is c. The square root of 9 is just 3. So since I only had 2 terms to begin with, we know that this is going to be a difference of squares that involves 2 quantities, 2 sets of parentheses. The first term in both of my sets of parentheses will be the square root of 16c squared, which is 4c. The second term in both of my sets of parentheses will be the square root of 9, which is 3. And because this is the difference of squares, we know that one of my sets of parentheses has a plus in the middle, while the other has a minus in the middle. And there you go. In our fourth example, we again have a trinomial, and we notice in this trinomial that my first term of 9s squared is a perfect square, and my last term, my third term of 25, is also a perfect square. So when I take the square root of 9s squared, we have a result of 3s, and the square root of 25 is 5. Now, since this is going to be an example of a perfect square, which we know because there are 3 terms, all A, B, and C terms are showing, then we saw in the introduction that our final result is going to be one set of parentheses, one quantity, that is squared. The first term is the square root of the 9s squared, where we found 3s. The second term will be the square root of the 25, where we got a 5. And then to determine what is going here in the middle, what sign should be here, we look at the sign on our B term. And that is what is going in there. So since there was a plus on this 30, we can put a plus right there in the center of our quantity. And there you go. Our fifth and final example shows us again only 2 terms with a minus in the middle. So this will be a difference of squares, and we are going to tear apart our 2 terms. The square root of 4g squared is 2g, and the square root of 1 is just 1. And since we have only 2 terms to begin with and a minus in between them, we know that this is the difference of squares, which has a resulting factored form with 2 binomials, where the first term in both of our binomials is the square root of our first original term, 4g squared, which was 2g. And the second term in both of our binomials is the square root of our original second term, which was 1, which is the square root of 1. And we remember that with our two binomials, we put a plus in between the two terms from one set of parentheses and a minus in between the two terms in the second set of parentheses. And there you go.